Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of quantum technology. In this series now we discuss the quantum sensing. This sensing is the detection and the measurement of the quantities or the changes in the quantities of chemical composition, light, motion, pressure, sound and temperature and any other physical quantities. So, quantum sensing we will discuss today. So, the wide ranging applications include healthcare, navigation and the scientific research as well as the various application of industrial interest. So, the accuracy of the measurement is crucial to performing analysis which influence the corresponding response to the detection as well as give the accurate result. Unfortunately, existing sensing technology is too limited for some of these applications. So, but for those applications, fortunately, novel quantum sensing technology offers unprecedented accuracy and precision in the detections and the measurement. So, there is a requirement of the accuracy as well the efficient detection and the accurate measurement. Quantum sensing is required. So, quantum sensing is an advanced sensor technology that vastly improves the accuracy of how we measure, navigate, study, explore, see and interact with the world around us by sensing changes in the motion and electric and magnetic fields. So, the analyzed data is collected at the atomic level. As we are talking about the quantum sensing, so we are analyzing the sensitivity and the measurement at the atomic level. It is called the quantum sensing because it uses quantum resources. It is a delicate phenomena that are apparent only on an atom sized scale to achieve the extreme accuracy at the atomic size molecules. So, quantum sensing is a technology using the principle of quantum mechanics to develop the new types of sensor. So, further we discuss about the sensors which uses the quantum mechanics. That is why it is called the quantum sensing. It lies under the quantum technologies category along with quantum computing, quantum simulation and quantum communication. So, quantum sensors are expected to have the higher sensitivity, accuracy, precision in their measurements of the physical quantity such as magnetic field, electric field, temperature, pressure, chemical composition. So, quantum sensing measure the physical quantities like magnetic field, electric field, temperature, pressure, chemical composition and so on. Now, next question, how this quantum sensing work? Collecting these delicate data at the atomic level. Why are we calling it as a delicate? Because we are talking about the atomic level. Often means extracting information from individual atoms instead of or from the huge collection of the atoms as happened in the classical physics. So, this allows quantum sensors to make our technological devices exponentially more accurate, more thorough and more efficient as well as more productive. So, whenever we switch from the classical to the quantum sensing, we are able to detect the sensitive result more accurately, more thoroughly, more efficiently, more productivity at the atomic level. So, devices that use quantum sensing are also not subject to the same physical constraint as conventional sensors, allowing for exceptional reliability with less vulnerability to the signal jamming and the other electromagnetic interference that is increasingly common for the today's light and sound based data sensors. So, how these quantum sensing work? So, what is the core principle behind the quantum sensing? Quantum sensing works operates on the principle of quantum mechanics, the principle that have been referred that can be referred as the as there is we use a quantized energy levels. So, like a foot on the rungs of ladder, quantum system have discrete energy levels and that they cannot be in between the. So, if we talk about the quantum sensing, so core principle of quantum sensing, first is the it use a quantum mechanics, second it is using the quantized energy levels. What is the core principle of quantum sensing? Quantum sensing is the measure of how long a quantum state can remain excited, which is the duration available to perform the measurement or the computation. So, a core principle of quantum sensing, first is the quantum coherence. As we have discussed in the previous, what are the main point whenever we talk about the quantum technology. So, similarly here in the quantum sensing, we use the quantum coherence. So, the measure of how long a quantum state can remain excited, which is the duration available to perform the measurement or the computation. Coherence means at up to the what limit we can measure it. Now, another is a quantum entanglement. How we use this quantum entanglement in the quantum sensing. So, two or more quantum systems becomes one quantum system with correlations and the anti-correlations affecting its components regardless of the distance. When we connect the two components which are apart, still we are connecting this component through the quantum entanglement. Another is a quantum interface. This wave-like nature of the quantum particles allows waves to constructively and together destructively cancel one each other. Similarly, in the interference, similarly here we talk about the quantum particles which allow the wave to constructively add together and destructively cancel one another. So, at the one time we get the maximum intensity, and other time we will get the minimum intensity or the zero when they are in the destructive mode. Another is a single photon individual energy packets. Now, another core point is the squeezed state, minimizes the certainty in the one property at the expense of the another. So, quantum sensors might leverage other quantum mechanical principle. After all, there are quite a few modalities that are used as a quantum sensors. They tend to focus on the specific type of application where we are using these quantum sensing to develop the quantum sensor. So, there are the two common approaches to quantum sensing. First approach is atoms and ions are trapped in a vacuum chamber and cooled to the low temperature. These are the common approaches for the quantum sensing. First is atom and ions are trapped in a vacuum chamber and they are cooled to the low temperatures. Then they are manipulated with the lasers to measure their physical properties while controlling their internal states. How are we controlling the internal state? By just changing its temperature. So, atoms and ions are trapped in a vacuum chamber and cooled to low temperature. Then they are manipulated with the laser to measure its physical properties while controlling their internal state. For example, by measuring the magnetic field, quantum sensor plays a small sample of the atoms and ions to be affected by a magnetic field. And as we are talking about the atomic level, so we can measure the very less magnetic field or a very low quantity of magnetic field through these quantum sensors. So, these atoms and ions will then split into different energy levels which can be detected with a laser as they will shine. By tracing patterns of fluorescence, researchers will assess the strength and direction of the field. What is the second approach? In the second approach, quantum sensor use individual photons properties to measure physical quantities. For example, sensors can measure the temperature with high precision by shining a laser beam and analyzing the intensity and the wavelength of the scattered light. So, quantum sensor use what we are called the quantum resources. How the quantum sensing extract data at the atomic level. This is the main question. Then how we can get the, how can extract the data, or we can sense the physical quantity at the atomic level. So, quantum sensor use the quantum resources to measure the change in the atoms with a higher degree of precision than any traditional measurement strategy. So, quantum resources are physical quantities that do not exist in the physical physical of the classical mechanics. So, which includes the entanglement, quantum interference, discrete state and the coherence. Means at the atomic level they just follow the interference, just they follow the entanglement as well as superposition and the coherence. So, if we take an example, so we can take the quantum optics typically relies on the measurement using the various aspects of the light or the photons, but quantum sensors can also be made from other medium such as atoms in the free space and the certain solid state devices. So, what are the benefits of the quantum sensing? Why we are doing? As we know that we are working on the particles of the atomic size. So, there is a requirement of the quantum sensing. So, what task quantum sensors can do, or what are the benefits of the quantum sensing? First is increase and improve the sensitivity by detecting, measuring and distinguishing different types of the physical quantities or the chemicals with the unprecedented sensitivity and with the high accuracy. Means quantum sensors can increase the sensitivity measurement in the increased and improved manner. So, we can detect the sensitivity by measuring the different parameters or the different physical quantities or the chemical quantities which are with the high accuracy, which are at the atomic level. Another, offer the high precision by making the measurement with extremely high precision to offer accurate and detailed measurement of physical quantities. Another, ensure non-invasive measurement by providing an accurate measuring without physically touching the object, which can be crucial in certain applications such as medical diagnostic. We can use the sensing as we require the real time data in the medical purposes. So, enable the fast response time by providing the real time management, allowing for immediate feedback and control in the variety of application where we are just required the real time or in situ calculation. We require the efficient result in which we can use the quantum sensing. Lead to the new application by evolving the rapidly with the new sensing techniques and application being developed all the time. So, this opens up the new opportunity for scientific research, medical diagnostics and environmental monitoring and so on. So, what are the type of quantum sensors which used as a quantum sensing devices that we will discuss. So, there are the various type of the quantum sensors like atomic clock, which are used in the quantum sensing devices. Atomic clock use the highly stable and predictable oscillations of the atom, such as cesium, rubidium atoms, to measure the time with extreme accuracy. So these clocks are applied to GPS navigation and the scientific research. Another is the magnetometers. Magnetometers are the properties of the atoms and ions to measure the magnetic field in the geology, medical diagnostics and the material science. Magnetometer are used in the various fields just to measure the magnetic field at a sensitive level. So, gravitometers, this gravitometer measure the gravitational field for the geophysics and the navigation purposes. Another is the interferometer. So, interferometer use the interference pattern to photons to measure length or the distance. So, these sensors can be useful for the metallurgy, microscopy as well as the precision engineering. What is a thermometer? It is also a quantum sensing device. So, thermometers measure the temperature with the high precision and accuracy by using the atoms and ions. So, thermometer can be helpful in area such as the material science, medical diagnostics and the food safety. These thermometers works at the atomic level. Chemical sensors, again chemical sensor detects the chemicals with high sensitivity specific in the environmental monitoring, gas sensing as well as materials present in the compositions that we can also measure through this chemical sensor. For the medical purposes, food safety, we use this chemical sensor. Another is a imaging sensor. This is imaging sensor uses the properties of the photons or atoms to create the high resolution images of the object or the material. So, these sensors can be beneficial for the medical imaging and moreover material sciences and the surveillance, because these imaging sensors can just measure the properties of the photon and the atoms in terms of the features. So, imaging sensors are also work as a quantum sensing device. Now, quantum sensings typically basically use the four phenomena. So, we can discuss it as first we can define the quantum sensing typically uses the described one of the following. Number 1, use of quantum object to measure a physical quantity, classically or quantum. So, quantum object is characterized by quantized energy levels. Specific example include the electronic, magnetic, vibrational state of the superconducting or the spin qubits, neutral atoms and trapped ions. So, use of quantum object to measure the physical quantity. Another use of the quantum coherence, that is wave like spatial or temporal superposition state to measure a physical quantity. Another use of quantum entanglement to improve the sensitivity or precision of a measurement beyond what is possible classically. So, first it measured the physical quantity, use of quantum coherence. Third, use of quantum entanglement to improve the sensitivity or precision of the measurement beyond the classical measurement. So, of these three definitions, the first two are rather broad and cover the many physical systems. This even include the some system that are not strictly quantum. So, an example is the classical wave interference that it appears in the optical or the mechanical system. The third definition, which is the most stringent and a truly quantum definition, since quantum sensor according to the definition 1 and 2 are often close to the application. So, we will mostly focus on these definitions and discuss them extensively in the further detail. So, while these type of sensors might not exploit the full power of the quantum mechanics, but the type third sensors, they already can provide the several advantages, most notably operations at the nanoscale that are not accessible to the classical sensor. So, type 3 sensor work on the quantum phenomena, that is a quantum, that is the quantum entanglement, that is the basically this is the quantum sensors. So, because type 3rd quantum sensors rely on the entanglement, more than one sensing qubit is required. As we are saying that is entanglement, so there is a requirement of more than one sensing qubit. So, a well known example is used of maximally entangled state to reach a Heisenberg limited measurement. So, then we will discuss how these quantum sensors work. So, what is the phenomena, what the equations we use, how we measure the physical quantity physically through this sensor, that we will discuss. So, the quantum sensing device which is very much used is the quantum sensor. So, quantum sensor leverages the principle of quantum mechanics with different sensors leveraging the different principle. Different parameters we can measure with the different sensor as per the application we require. Like photonic sensors leverages the quantum entanglement, single photons and the squeezed state. We have defined the various parameters. So, if we talk about the photonic sensors, it take the leverages of the quantum entanglement, single photons and the squeezed state, and are often used to measure the electromagnetism and it detect the vibrations. Another is a solid state sensors. For another example, leverage the quantized energy levels and the quantum coherence to detect a stimulus or measure the quantities. What are the other sensors? Leverages the like the quantum interference or the other quantum mechanical principle. So, as per the requirement and as per the applications, the various leverages taken by the various parameters or the various principle followed by the quantum sensor. So, as a quantum technology advancement in the quantum sensor can impact the other quantum technologies. A neutral atom quantum sensor module, for example, if we take it as the quantum computer trap. So, a magneto-optical trap, that is the MOT, are the both ultra high vacuum chamber with the cloud of the atomic vapor. Both technology apply the and focuses the laser beam to these clouds, and these methods are used just to cool down the atom, and they are used in the superconducting devices. Thank you very much.